There we go. All right, stuff we didn't cover last time were combinations and permutations. But in order to describe what those are and how they work, we need to quickly introduce a notation that you may or may not have already seen before. It's called the factorial, and it's denoted like this. In this case, for this class, all of our n's, they're all going to be integers. We're not going to worry about factorials of decimals. You can do factorials of decimals, but that requires the gamma function, which is a much higher level mathematical course and concept, typically reserved for graduate students and whatnot. And this is most clearly not a graduate class, so we're not covering that. And besides, it has no impact either way, even if I taught you it. Now, the layman's definition of the factorial is this equal to the product of all of the integers equal, well, basically the integer value n and the product of all the integers below it. So n times n minus 1 times n minus 2, blah, 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 all the way down to times 2 and times 1. Now, as a note, let's say our n is 2, then it's just 2 times 1. If our n is 1, it's just 1. And the idea behind the factorial is it is essentially a formula to show you how many ways you can arrange n objects. So if I have 3 cards, and let's say they're the ace of hearts, king of hearts, and queen of hearts, we can go ace, king, queen, that's 1. Ace, queen, king, that's 2. King, ace, queen, that's 3. King, queen, ace, that's 4. Queen, king, ace is 5. Queen, ace, king is 6. 6 ways, 3 times 2 times 1. That's the idea behind the factorial. Now, I'm going to put this in notation that you will probably recall from Unit 1. We can use our product notation from 1 to n of I. That's the product notation. Now, these are just bounds. This means we start at 1 and we go up to n. So in this case, we'd have I is 1, that's 1. Then we go to I is 2 times 2. So 1 times 2 times 3, so on and so forth. Pick whichever notation is easier for you. So for example, let's say I asked you what's 5 factorial. 5 times 4 times 3 times 2 times 1, that's 120. Okay? Now that we have the factorials, we can explain combinations and permutations. So here I'm going to, I'll say what it is, and then I'll type it out with my 2 hands so we can go a little bit faster. So combinations are selecting n objects, like lowercase n, from capital N objects where the order does not matter. So I'll type that out for you right now. Okay, so we select n objects from n objects, like lowercase n versus uppercase n. It is implied that lowercase n is always less than or equal to uppercase n. Oh, come on. And there we go. It is always implied that lowercase n is less than or equal to uppercase n, because you can't select 10 objects from 9 because you don't have 10 objects. You only have 9. Now, we denote this as C of lowercase n, uppercase n. So the C stands for combinations. Lowercase n means we're choosing lowercase n objects. And then the uppercase n means it's from these n objects. It is implied there's no replacement. That's implied. Okay? And now there's a formula for this. And this formula is equal to capital N factorial divided by lowercase n factorial times capital N minus lowercase n factorial. So for example, let's say we had those 3 cards, the ace, the king, and the queen. And I said, in how many ways can we pick 2 of those cards where the order doesn't matter? Capital N is 3, lowercase n is 2. So we would have 3 factorial divided by, we're choosing 2, that'd be 2 factorial, And then we have 3 cards total, so 3, and we're choosing 2, so minus 2 times 1 factorial. 3 factorial, 3 times 2 times 1, that's 6. 2 factorial is just 2, because 2 times 1 is 2. 3 minus 2 is 1. 1 factorial is 1. So 6 over 2 times 1 is 3. 3 ways to do it. Intuitively, that checks out. Because we have 3, we choose 2. We can have ace and king. We can have ace and queen. Or we can have king and queen. And notice here the order does not matter. On the other hand, if I asked you, does the order matter? Then that changes things. Because it could have been ace and king, or it could have been king and ace. Let me pull this up. I mean, I don't know what I can do about a little bit of lagging. Sometimes if you're all on the same internet connection in a residential dorm, you can have the same lagging issues. Now, I just gave the example where order does not matter. Obviously, the question that I just raised is what happens if order does matter? We have a term for that, and it's called a permutation. I'll read it out to you, and then I'll type it out. And a permutation, again, we start like before. We select lowercase n objects from capital N objects. But this time the order does matter. So I'll type that out for you. Oh, come on. All right, there you go. So we select lowercase n objects from uppercase n objects where order does matter. So when we're picking those 2 cards, if I said I want to know which one came first, now the order does matter. Again, with permutations, we're assuming no replacement. Because if there is replacement, you just start with your base probabilities, and you can use the probability laws from the previous chapter. Like with the combinations, we have a notation for this, and we call this permutations as capital P of lowercase n, uppercase n. I might ask, hold on, we use this P already. We use it with the probabilities. So I'm confused now. If it helps, think of it this way. Unless that capital P has these 2 n's on it, you can assume we're dealing with the actual probability. So if you have a P all on its own with nothing, no subscripts or superscripts, we assume it's probability. We have a formula for this. It is very similar to the one for combinations, and it is capital N factorial divided by capital N minus lowercase n factorial. The only difference between permutations and combinations is that with the combinations, we divide by the lowercase n factorial as well. So with the example of those 3 cards, we have the ace, king, and queen. Let's suppose that we want to pick 2, but we care the order that we pick them in. So we have 3 total cards. So we have 3 factorial. And now we still have 3 cards, capital N, and we're choosing 2. So lowercase n is 2 factorial. So in that case, 3 factorial is still 6. 3 minus 2 is 1. 1 factorial is 1. 6 different ways. And you'll notice that 6 checks out with the example we gave at the beginning. Now, in the example at the beginning, we should n factorial. The reason why this happens to match exactly is because we picked every single card except for 1. Now, a question you might ask yourself is, okay, what happens if we have 0 factorial? What happens if we're picking nothing? Or what happens if n minus n is 0? What now? With the idea behind the factorial, it's how many ways we can arrange all of our objects. So we had 2 objects. You can do it 2 different ways, front and back. With the 3 objects, I already explained that. With the 4 objects, let's say A, B, C, D, you can go A, B, C, D, A, B, D, C, A, C, B, D, so on and so forth. That'll come out to be 24 ways. Let's say you have nothing. How many ways can you order nothing? 1 way, nothing. So in this case, we say that 0 factorial is equal to 1. And there are other ways of proving why that's the case. And I can do that if you want. But the easiest explanation is just the more intuitive one. If you have nothing, there's only one way you can order nothing, and that's nothing. Yes. The capital N, I'll write that down. Capital N is how many, is basically the size of our sample. It's our sample size or sample space. Lowercase n is what we're taking out of it. So I'll write that down. That's a good point you brought up. Okay, there's that. Then lowercase n equals the number of objects. Let me make that a little bit lower. We are choosing. There you go. There's difference. Yes. You have a question? Okay. Yes. Exactly. So the example she gave, if we had 5 cards and we're picking 2, then our capital N is 5 because we have a total of 5 cards to pick from, but we're choosing 2 of them, so that would be 2. If I had a deck of cards with me, I would show you and then do a card trick probably, but this is a math class, not a magician's class, so we're not going to worry about that. Maybe if we have more time next week, we can try that. So, any question about this notation or whatnot? Yes. Pardon? Yes. So we have the 3 factorial, and that's 6. That makes sense? Now we have 3 minus 2. That's 1. 1 factorial is 1 because we each have 1 times itself. So 1. So we have 6 over 1. That's 6. Pardon? So if the 5 is in place of the 3, that means the 3 at the top will also have to be a 5 because both of those 3's are our capital N. Yes, so I'll make that a little bit clearer. There we go. I keep forgetting to bring my mouse pad. All right, so we'll go over an example and then we'll get into chapter 5 stuff. For those of y'all at home, it won't affect you because I can just update the whiteboard while you're here. For those of you in person, I would recommend writing down this problem, and then once you all have it written down, you can let me know, and then while y'all work on it, I'll get the whiteboard for the remainder of the lecture. It's really just copy-pasting problems. That's all it is. So go and write this problem down, and then I'll stop the projector sharing and then get the other one updated, and then we'll switch to that one. So you'll have probably 3 minutes or so to work on this one. In this case, for both of these parts, I'd recommend first identifying capital N and then identify lowercase n. For those of you who are at home, you can just instantly start working on it because the screen share will keep going for you. So you don't have to worry about anything. All right. Is there anyone in person who still needs a little bit of extra time to write down the problem? Okay. All right. Anyone need some more time to write it down? Okay. I'm going to stop the projector sharing for just a moment. I'm going to switch over and get that one updated, and we'll go over these answers once that whiteboard's ready to go. right, you'll have an extra minute or two. All right, let's go ahead and pull this back up, I believe. For the people that were in Zoom, it's stayed the same the entire time, right? Hopefully it didn't switch on y'all or anything. All right. Okay. So with this one, with both parts, let's start by identifying our capital N. We'll just ask people in class, how many do you think the capital N was 10? 3? 7? Something else. Our capital N is 10. So for both these, capital N is 10. And so therefore, our lowercase n, how many of y'all think it's 10? 3? 7? Something else. It is 3. And the reason why our capital N is 10, we have 10 people we can pick from. The reason why lowercase n is 3 is because we're actually choosing 3 of them. So let's start with part A, right up here. And we're going to choose 3 people, and the order does matter. So in this case, how many of y'all think it's going to be combinations? How many of y'all think it's going to be permutations? That is correct. It is going to be permutations. We recall the definition of permutation says we're picking n from n, or lowercase n from capital N, where order does matter. So in this case, our notation will be permutations of lowercase n, capital N. So in this case, we just need the value of P of 3, 10. So that's our notation. And we recall in this case, we have 10 factorial over and n minus n, so 10 minus 3 factorial. Now we're gonna do I'm gonna do a little bit of an algebraic shortcut. 10 factorial is equal to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 7 factorial. Don't worry, I'll write down the general formula for this in a moment. And 10 minus 3 is 7, so 7 factorial. Instead of having to calculate this all out, we just cancel out our 7s. So these just cancel out. You're going to want to do this when you get to the really big numbers. You could have done this with your calculator, that's fine. But when you get to 20 factorial, 30 factorial, your calculator can't handle it. It's too big. These get really big really quickly. So we should have 10 times 9 times 8. 9 times 8, 72 times 10. We have 720 possible ways. Yes. Pardon? 7 from where? So 10 minus 3 is 7. So our denominator is 7 factorial. You got that? Where that makes sense where that came from? Now, any factorial, let's say we have 10 factorial. That's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, 7 times 6 times 4 times 5 times 3 times 2 times 1, that can be written as 7 factorial, right? So we can say that 10 factorial is equal to 10 times 9 times 8 times 7 factorial. That makes sense? And now, since we have a 7 factorial in the numerator and a 7 factorial in the denominator, we should cancel them out. Because technically, 7 times 6 times 5 times 4 times 3 times 2 times 1, I believe, how much is that going to be? It's going to be, I think, like around 4,900, somewhere in that ballpark. Maybe 50-40? 50-40 sounds right. But regardless, we'll have 50-40 in the denominator, 50-40 in the numerator. They're going to cancel out. So general rule for this, and you can write this down if you want. It's up to you, but it will make life easier on you. We can say that n factorial is equal to n times n minus 1 factorial. And likewise, if you want, you could say that, likewise, you could say it's equal to n times n minus 1 times n minus 2 factorial. This will make your work a little bit easier on you when you're doing the algebra. Now, if you didn't want to do that here, that would have been fine. You still would have gotten the correct answer. So now let's do part B. In this case, order does not matter, so it's going to be combinations. So we can denote this as C of lowercase n, uppercase n. Let me close this because this PC is overheating a little bit right now. And lowercase n. So here are our formula for combinations. We have capital N factorial. So 10 factorial. Divided by, we have lowercase n factorial, so 3 factorial. And then we still have this 10 minus 3, so 10 minus 3 factorial. There we go. Sorry, make that a bit easier. Here, the process is going to be the same. We have 10 times 9 times 8 times 7 factorial. Denominator, we have 3 factorial, that's 6. And then 10 minus 3 is 7, so 7 factorial. So we see these 7 factorials are going to cancel out again. We know 10 times 9 times 8 is 720. We can divide that by 6. 720 over 2 is 360. Divided by 3, we get 120. All right. Any questions about this? All right, we're going to move on to our chapter 5 stuff. So let me switch the screens. All right. So first, we're going to introduce types of random variables. There's 2 types of random variables, discrete and continuous. And this is kind of going to be a little bit reminiscent of quantitative versus categorical. But the catch is these are both quantitative. With discrete random variables, we have a finite number of results. So for example, the ACT scores, it's 1 to 36, 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 blah. That would be discrete. There's only so many of them. A continuous random variable, there's an infinite amount. We can go from 0 to theoretically millions and millions and millions. We can go as far into the decimals as we want. So I'll type those out for you. There we go. Let me move this to the right. And here I'm going to abbreviate random variables as RV. Okay. So those are different types of variables. So for example, the ACT scores are an example of a discrete random variable. Whereas, say, the time it took you to get to class today, that's going to be continuous. It could have been exactly 14.1 minutes. It could have been 13 minutes, 50 seconds, and then an additional 0.1563 blah, 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 blah seconds, whatever you want, as long as it's greater than 0. So that's continuous. And that one's discrete. Let me pull up the chat. Where's chat? Yes, we're doing chapter 5 right now. Yes. We just covered the remainder of chapter 4 that we didn't get to. So let's just go straight to a practice problem right now. Here we go. Practice problem right here. Let me zoom in for those who are in person so you can see it easier. So you should only need maybe 30 seconds on this one. A couple of random variables, figure out if they're discrete or continuous. You should need no more than maybe 15, 30 seconds to figure this one out. All right. Number one, how many of y'all think that is discrete? Continuous? This one's going to be discrete because you can't have half of a car. I mean, technically you can, but then the car crashed in the toll booth. On the other hand, they're all integers, and theoretically you could have hundreds of thousands of cars arrive in one toll booth. That'd be pretty impressive, but obviously you can't have tens of millions of cars. It's not physically possible. Second one, how many of y'all think that's discrete? Continuous? Yes, this one's continuous because when you see time is pretty much always continuous because time can go in as far into decimals as you want it to. It can pretty much go as far out as you want it to as well. So this one, I'll just write this down. Discrete, continuous. All right. Now, today we're going to focus primarily on, let me zoom out a little bit. We're going to primarily focus on the discrete distributions. And then next week, we will introduce the continuous ones. There are quite a few types of discrete ones. We just have general discrete, which oftentimes might be general discrete. We have discrete uniform. It's a special case. We'll have the binomial. We'll have hypergeometric. And then we'll have the Poisson distribution. But for now, let's just focus on a relatively boring one. Let's say we're rolling a die. It can go from 1 to 6. So in this case, we have 6 possible die values. Oh, that is a very not flat line. There we go. Close enough. Doesn't have to be that far. Okay. So we can have a 1. We can roll 2. We can roll 3. We can roll a 4. We can roll a 5. And we can roll 6. So then the probabilities of this, we'll call this P of xi. In this case, it's 1, 6. So 0.166, blah, 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 blah. 0.166, blah, blah, blah. So on and so forth. They all have the same chance of being rolled, assuming it's a fair dice. Let me get rid of that 0. We don't need that. There we go. So 0.166, 0.166, 0.166. And again, you'll notice this already satisfies our probability laws from chapter 4. All of these probabilities add up to 1, and all of them are from 0 to 1. So this already satisfies those 2 laws. Now you'll notice all of these have the same probability. This is a special case of a general discrete distribution, and it's called the discrete uniform. So this is a discrete uniform distribution. And we can say that this probability is equal to 1 over n. We have 6 data values, so we had 1, 6. That's 0.1666666, blah, 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 blah. So here, let's do a couple of quick practice ones with this. And here, I'll do these ones, and then you'll have one on your own you can do. And note, when you have the practice one, the values won't all be the same, but the process is going to be the exact same. So here, let's suppose I asked you for part 1, what is the probability of rolling a 1? Well, probability of rolling a 1 is equal to P of 1, 0.16666. For web work, you can round that to 0.167, and it would take that. Okay? Likewise, you can put 1 over 6. Web work will take that as well. Now, let's suppose part 2, I asked you the probability of not rolling a 5. You recall that notation, the tilde means not. You can use 5 with the capital C in the top. It's up to you. We're going to stick with the not because that's a bit more Englishly intuitive. Well, we recall we can use the complement rule. The probability of not rolling a 5 is equal to 1 minus the probability of rolling a 5. That's our complement law from chapter 4. You should remember that. So in this case, probability of rolling a 5, 0.166666. Let's call that 1/6. The same thing as 1/6 because we have our 1 over n. 1 minus 1/6 is 5/6. And so that's that probability. Okay? Now, let's suppose I asked you what is the probability of rolling a 1 or a 5? Well, we recall from our notation that's equal to the probability of rolling a 1 plus the probability of rolling a 5. So 1/6 plus 1/6. That's 1/3, which I can write that as 0.333, so on and so forth. In web work, you can put 0.333, and it'll take that. And finally, let's suppose now I asked you, what is the probability of rolling at least a 5 or higher? So the probability of rolling at least a 5 or higher is the probability of rolling a 5 or a 6, which is equal to the probability of rolling a 5 plus the probability of rolling a 6, which is 1/6 plus 1/6, which is equal to the same answer we just got. Before I continue, does it make sense what happened here? We just took this discrete table and used our laws from chapter 4 to get the answers. There's a reason why I say this unit is just really one big chapter. It's just one big gigantic chapter. Now you'll notice we were talking about those lines as our motivating example, and to stick with that, obviously a question you might ask yourself is, well, in this case, this is a discrete uniform, and the motivating example we use, we assume it all has an equal chance. And generally speaking, that'll be the case, but sometimes that's not going to be the case. Usually maybe 90% of the time, it won't take any longer than, say, that 5 minutes. But every now and then, maybe 10% of the time, you'll go straight up to that 7. And that is not a uniform distribution. And we'll talk about non-uniform distributions very soon. So let's go to a practice problem with a discrete one. And that is, well, you can do both of these actually. So I'd recommend we'll start with problem 3 so you get used to how these tables work. Notice this one's vertical. You can do vertical or horizontal. It's up to you, whichever you prefer more. So here we have this probability distribution. I'm changing that to a P, make it easier on you. Let's make that a P. There we go. Even better, let's just throw out the F entirely. There we go. And make that a P because we're trying to stick with the P because that makes more sense. Okay. So here, just do the same thing that I just did, but with these different numbers. So I'll give you about a minute or two to work on this. Then we'll go back up that example there, and then we will move on to our next distribution. Now you'll notice that with many of these, there are a couple of ways you can do it. I recommend picking the easiest one, but if there's multiple ways, then I'll show you how to do it. I'll show you how to do both. Definitions of what, Kylie? Kylie, are you referring to the definitions for the types of random variables? Does anyone need more time? Okay, we'll go an extra minute. Okay. Let's go ahead and go over some of the answers, or all of them for that matter. So, part 1, or I'll just say part A, whatever, don't really matter. X is exactly 1. So this is equal to the probability that X is 1. And that probability is 0.2. Part 1 was a reading question, not a math question. Y'all know from the first assessment, and you will know from future ones, there's a bit of reading questions here more than anything else. Part 2, we're asking X is at most 2. So essentially, this is asking us the probability that X is less than or equal to 2. There's 2 ways you can do this. You can say 1 minus P4 plus P3, or we can just go straight up. We'll just go straight up because that one's a bit more intuitive. So this is equal to P0 plus P1 plus P2. P0 is 0.1, P1 is 0.2, and P2 is 0.4. This is 0.7. Now 3, it's saying X is between 2 and 3, endpoints included. So essentially it's asking us, what's the probability that X is 2 or 3? So this is asking us the probability that X is 2 or 3, which is equal to the probability of 2 plus the probability of 3. Now you'll notice this is the exact same as one of our laws. That's a shortcut. Technically, the full law, we have to subtract the probability of 2 and 3, but we know these are independent because you can't have 2 and 3 cars at the exact same time. It's 2 or 3, so that's pretty implied it's independent, so we can use that shortcut. So P of 2 is 0.4, P of 3 is 0.2, 0.6. Now the last one, there's 2 ways you could have done it. One of them, it's the brute force one. The other one is using the complement. The brute force, we add up everything that's not 0. So 1, 2, 3, and 4. That'd be 0.2 plus 0.4, so we're up to 0.6, plus the 0.2, that's 0.8, plus the 0.1, that'd be 0.9. That's the brute force. Let's use one of our laws instead. So this is asking us the probability that X is greater than or equal to 1. That's the same thing as saying 1 minus the probability that X is 0, complement law. So that's 1 minus 0.1, so 0.9. Are there any questions about this problem? Okay, we'll go back up to that one right before. Now you'll make your own table. And in this case, let's suppose you just flip a coin once. You just flip the coin once, it's heads or tails. Make the probability table for that. You're only going to have 2 entries, one for heads, one for tails. This should take you no more than maybe 15 seconds to do. I'll give you a little start. The way to start your table out is like this. This is how you start your table. So fat, fill in the bottom row, and then we'll go over that, but that'll be pretty easy. And then we'll move on to some more probability laws. Anyone need more time? All right. So here we always have the P of X right below it. Or we can just put Xi, it doesn't really matter. We'll put Xi just for it. Flip a coin, even chances, 50-50, 0.5, 0.5, that's all there is to it. If we wanted to, we could expand this to flipping the coin twice, in which case the probability of one head would be 50%, odds of no heads, 0.25, odds of both heads would be 0.25. All right, now I'm going to give you a few extra laws. We're going to go down here to write them. So this is mainly these are mostly ones to help make the work easier on you. So let's suppose I asked you for the probability that our x is greater than or equal to xk. You might ask, hold on, what's xk? Same as before. Xk, in the case of that example we did, xk could be 1. So that'd be the second data value. So asking you, what are the odds of getting that data value or higher? This is equal to the probability of xk plus the probability of the next one, and so on and so forth, all the way to the very biggest one. So we're just adding up the probabilities that are all at or greater than that value. In this case, the k plus 1 means this value is greater than the 1 at k. So this is like when remember we order the data in the previous unit. Think of this like the data being ordered. And to put this in summation notation, we take the sum of our probabilities at xi. Oh, that's too big of an I. At xi, where here, our boundaries, we start at k, and we go all the way up to n. Choose whichever one is easier for you to remember. If you're trying to put as much into your cheat sheet as possible, and you can remember the summation notation, then obviously the summation notation will save you a bit more space. Pick whichever one's best for you. Now, by the same logic, let's suppose I asked you the probability that x is less than or equal to xk. Well, in this, we start at the lowest value. Our very lowest one, x0 corresponds to our lowest. And then p of x1, this is our next lowest, so on, so forth, all the way up to whatever xk is. I might say, hold on, this is the first time I've seen x0. All the times before we started at x1. And that's true. The reason why is because all the times before we never had 0, ever. Like all of our data values were actual like existing numbers. Whereas here, sometimes you're asked the probability of the thing never happening at all. That's basically the probability of nothing. So now we have the x0. That's why we have this extra 0 now. And again, if you like summation notation, we can say the summation of p of xi. In this case, we now start at 0. Sorry about that. And we go to k. Now, let's say I asked you the probability of it being greater than xk. The only difference is in that case, we just take this term out and we keep going. Likewise, for the one below, if I asked you it to be strictly less than xk, all you have to do is scratch that out. Okay? And finally, we're going to adapt our complement law to the most general form of it possible. This is going to be about as general the complement law as you can get. The probability of our x value being greater than our lowest value, so basically existing, is equal to 1 minus the probability at our lowest value. By that same logic, the probability that we're not the highest value is xn. We recall it's capital N because that's how many we have to pick from, is equal to 1 minus the probability at that xn. All right. Now that we've done that, we're going to get into our 3 distributions. The first one, we're going to start with the one that requires the least amount of writing. And this is called the Poisson distribution. It's a very fancy French name because the dude it's named after is French. So let's go over to the right-hand side. So we have the space. So our first of 3 distributions we'll talk about today is the Poisson distribution. It's not the Poisson distribution. This is a fancy French guy, and you know the French people, they like adding an extra 50 syllables to their names because they're fancy. Maybe if they spent more time winning wars, not having fancy names, they'd be better off, but is what it is. So in this case, the formal definition is the probability of the Poisson distribution at some value x is equal to mu to the power of x times e to the negative x, all divided by x factorial. I'll explain what these letters mean in a moment. Now, many of your standard scientific calculators aren't going to be able to calculate that very easily. On the exam, unlike the assessment, you will be allowed to have tabs open. Now, everything has to start out closed, but you'll be allowed to open them. There's a calculator I strongly recommend you use. It's called Desmos. And I will show you that right here in class today. And you can use that to very easily calculate this. You'll be able to use it, and I strongly recommend that you use it on the exam. Now, you might ask, hold on. If you allow these open tabs, people are going to cheat. Well, no, it tells me if you open a tab or not. So if you try to pull anything fancy, it'll say it. The reason why I didn't have the open tabs and whatnot on the previous one is because it's very easy to get the mean with those calculators, and then you're not learning anything. Now, what do these letters mean? In this case, our mu is equal to the mean. So, or the average number of whatever. In this case, our x is the point in question. And finally, E is Euler's number. How many of you have not seen Euler's number before? Okay. This one is 2.71 blah, 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 blah. What I'm going to do is pull up, let's just do a new window. Let's pull up Desmos. Here we go. Pull up the calculator. Those of you at home, I'm going to switch this calculator so you can see it right now. Oh, come on. There we go. I'm going to switch it to this. This right here. Yes, it was negative x, yes. This is Desmos. That's the link. You can write that down if you want. You will be allowed to use this on the midterm exam. So in this case, I'm just going to type in E. On the midterm exam, same thing. There you go. There's E. That's the entire full number of it. You don't have to write it down because you're going to be allowed to use Desmos. You can just type in that E. In fact, if you want to, you can never learn what that E even means. As long as you know how to type it into this calculator, you'll be fine. If you want to write out that full number, you're more than welcome to. It's entirely up to you. Now, we have 3 requirements to be able to use this distribution. So let me switch back over to our whiteboard. We have 3 requirements for this. And what I'm going to do, I'm going to type them out and then I'll explain them. So let's get our big box. I'm going to start typing. Oh, that's not changed. All right. These are our 3 conditions. First of all, if we're dealing with intervals over time, basically Poisson is for our intervals over times. For example, let's talk about those lines, say, at Whataburger. What are the odds if, say, you arrive somewhere between 9:45 p.m. and 10 o'clock p.m. that there's exactly 5 cars? That is an example of when you could use the Poisson distribution. Now, we are assuming that the probability of success doesn't change over time. You might say, what does success mean? What's a success? A success means we hit X. So for example, let's say our X value is 5. In the Whataburger example, that's 5 cars in front of you. If there's only 4 cars in front of you, that's a quote unquote failure. From your perspective, you'd rather have 4 instead of 5, but the perspective of the Poisson distribution, success means you get exactly that X value. Now, occurrences or non-occurrences essentially means, do we have 5 cars or do we not have 5 cars? That's what that means. Are independent over time. You'll notice this independence thing is a bit of a pattern here. Most of these assume things are independent. I will show you a distribution where it doesn't care about independence or not, but that's the hypergeometric. That's a very fancy one with a lot of nasty factorials. So before I continue, does it make sense? Like, does the general contours of this Poisson distribution make sense? Yes. Pardon? 3 of what? Conditions? Yes. The first one is for use of intervals over time. That's the first one. Yes. Because that one, if you can't even say yes to that, there's no point in answering the rest of them. You can answer the rest as much as you like. If you don't satisfy that first one, end of story. Now, I'll do some examples with you. Let's say the Whataburger example. Let's say at any given point in time, on average, there's 5 people in front of you. And you want to know the odds of there being exactly 5 people in front of you. So let's pull this formula up in the Desmos. And what I recommend you do is when you're typing this in, doing your assessment, you can just put in the arbitrary formula and put in the numbers. So here, oh, I have to switch the Desmos. Let me switch the Desmos. Stop share. Switch to Desmos. All right, here we go. So we recall that it is mu to the power of x. So in this case, our mean was 5. And we want to know the odds of getting exactly 5. So we raise this with the caret to the power of 5. And now we have e to the power of negative x, so negative 5. And now we divide this by x factorial. X is 5, 5 factorial. You'll notice it does the factorial for you, which I imagine for many of you will make you very happy. I don't care if you show yourself writing out the factorials. I just care that you know what each thing is and you know what formula to use. I'm not here to assess memorization. I'm here to assess understanding. So in this case, there's our number. In that case, the probability of getting exactly 5 cars in front of you is 0.175467, blah, 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 blah. In the case of web work, you could put in 0.175. That's it. Now, I don't remember off the top of my head if web work has a Poisson problem. The exam will, and the practice exam does as well. So let's use another example. Let's say I asked you, what are the odds of having 3 cars in front of you? The only thing that changes is that our x's go from 5 to 3. So we had mu to the power of x. That 5 is now a 3. We had the negative x, so that negative 5 is now a negative 3. And the 5 factorial is now a 3 factorial. I must have typed in something wrong there. Did I type in something wrong? Yes. No. The mean's still 5. So you might look at this yourself. That makes no sense. Here's what this means. There ain't going to be 3 cars in front of you. Because let's say we graph the Poisson distribution. Let's graph it for any value of x. Okay? So we had mu to the power of x. So 5 to the power of x times e to the power of negative x divided by x factorial. You'll notice by looking at this, our mean is right around here at 5. If we had 4, that's about 0.486%, I believe. Yes. The idea behind the Poisson distribution is that the further and further away we get from the mean, usually in the positive direction, the less likely it becomes that it'll actually happen. Only pull up the chat. Where'd the chat go? What is this thing doing? Well, because we just said it was. We said the mean was 5. We had an average of 5 cars. So, on the other hand, let's say I asked you what the probability of having 6 cars was. In this case, our x is now 6. And now we change that to 6 factorial, about a 5% chance. So, with that said, and notice, let's say I asked you what are the odds of 5 cars or 6 cars. The odds of 6 cars was 5%, roughly 5%. The odds of having 5 cars, I believe, was about 17%. So we'd add those two and we'd get 22%. Okay? So now let me switch back to this. I'll give you a practice Poisson problem. Oh, this is going to be further to the left. Here we go. Practice Poisson problem. Let me share the screen for those of y'all in Zoom. All right. So here's practice one. What I recommend you do, if you're on Zoom, this will just stay. If you're here in person, don't worry about the stuff at the top. The point of the stuff at the top is saying that we can use Poisson. So if I were you, write down the stuff in big black. Then I'll stop sharing for a sec, because I think there may have been a problem that I forgot to copy paste. So I'll give you just a sec to write down the stuff in black for those of y'all in person. And I'll give you a couple of minutes to work on it. I'm going to change this 5 to a 1. Make it a bit easier on you. Or even better, we can do 2. No, we'll just do 1. All right. I'll give you all a sec to write that down. Do any of y'all need a little bit of extra time to write this down? Okay. Let me turn that off for a second. I'll give you all a moment to work on that. Found it. All right. That makes sense. There was a slight error in the formula that I wrote down. That makes sense because that number shouldn't have been above 1. Let me correct that for y'all. Over here, this formula, I apologize. This should be a mu. That makes sense why those numbers are rolling above 1. I apologize. This is supposed to be mu. Sorry about that. Pardon? Oh. There we go. Come on, pop up. There you go. Sorry, that X is supposed to be a mu. I'm sorry. I knew something wasn't quite clicking there. Yes. Pardon? I'm sorry, can't quite hear what you're saying. So this right here, I changed that X to a mu. That's supposed to be a mu. So the e to the negative mu is always the same. So to give you the example, now we'll go back to Desmos, and now this will make much more sense. Yeah, this is going to make much more sense to me now. Yep, that's how it's supposed to look. Yes, that is how it's supposed to look. Very good. I apologize. Let me switch over to y'all in Zoom. Let me switch to the Desmos. This is what it's supposed to look like. I apologize. So now in the case of the Whataburger example, you'll notice what happened is when we changed that, the stuff to the right didn't really change. It was the stuff to the left. So going back to the example of 5, we now see this is supposed to be 5. That's funny. So in this case, actually the mean example still stayed the same. But now what happens? Now let's say we ask if only 2 cars arrive. You can now see the odds of 2 cars arriving. Oh, I'm sorry. That still stays as a 5. Sorry. There we go. Odds of 2 cars arriving were only 8%. There we go. That makes sense. I apologize about that. I miswrote that on here. But I'm a miswrite. So I was looking at that Desmos and that didn't look right to me. All right. I apologize for the bit of confusion. So now we will go back to that example. And now we will do the example and we will stick with what we had, the 5. That is why I had that as 5. This is why I should have had that. There we go. All right. Now I'll give you a couple minutes to work on that. I sincerely apologize for writing that down incorrectly.
Yeah, we can't kind of see.
Oh, yeah, I have to switch. I'm sorry. I have to switch back. I apologize. Here we go. Sorry about that. The mean is still supposed to be 5. We will do the hypergeometric distribution next time because next time wasn't expected to take the full class lecture anyways. So not that big of a deal. I'll write down the link here as well, so you have it on the whiteboard and for your notes. And you can use that on the exam, and you should be able to use that on every single future assessment and exam as well. John, were you in the restroom when I made the correction of the Poisson distribution? Were you in the restroom when I made the correction of the Poisson distribution? Okay, the Poisson distribution, if I go to the right over here, this x is actually supposed to be this mu. So I was going through, we were going through the examples, and I'm like, that probability should not be over 1. Because all the stuff to the right was fine, the stuff to the left wasn't. That's actually why I stopped sharing the projector, because I wanted to pull up the textbook to double check I had the right formula, and I had the wrong x written down. So, but now it's correct. Now that makes sense. The funny thing is, when we were doing the first one with the example of 5, it was actually still correct because in that case, our x was the mean. So it didn't matter if it was mu or x in that case. Pardon? So here, the mix-up was right here. That's where the mix-up was. I had a negative x there. It's supposed to be negative mu. That's where the mix-up was. Yeah, so when you're, say, working with this on, say, Desmos, the only two things you'll have to change are these two x values. The rest will stay the same. Does anyone need some extra time? Okay. So first of all, in this case, our mu is 5. So our base formula, our Poisson base formula, this should be a row. That doesn't really matter. Our base Poisson, we have P of x. Our mu is 5. So we have mu to the x times e to the negative 5 divided by x factorial. This is our base. So in the case of part A, we're just going to plug in x equals 4. So in this case, this will be 5 to the power of 4 times e to the power of negative 5 divided by 4 factorial. If you type that into WebWork, it should accept that. Just outright calculate that for you. But to switch over to Desmos, and I will do that right now. So let me switch over to Desmos. A lot of screen switching today. In this case, our mean is still 5, but now our x value, we're asking for exactly 4. So there we can see roughly 17.5% chance that we have exactly 4 arrivals in that case. Now, here's something you can do. If you want to pre-type things out, here's how you can pre-type, because on the exam, you'll have a general Poisson problem and multiple parts to it, kind of like that. Something you can do is your mean, the mean's going to stay the same for the entire problem. Let's just say our mean was 5 in this case, or it could be 10, doesn't matter what. It'll still be the power of negative x. Let's just put negative a for the time being. We'll add that slider. Our e to the negative 10 stays the same. And then we divide all this by a factorial. Now you can see what I can do here is just change it like that and make things easier. Oh yeah, that's fine. I can make things easier when typing in these values. You can see it's very goofy looking. Oh, because that's supposed to be a positive. Sorry, positive. There we go. So here, all I have to do, I just have to change the A. Just like that. Makes it nice and easy. If you want, you can do that, or you can do it manually. It is up to you. Now, I'll just read it out. For those of you at home, you already have it written down. We want the probability of at least one car. Well, here's the catch with Poisson. Poisson theoretically goes as high as we want. We can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Doesn't matter where the mean is. We're here. This is a perfect example of where you want to use the complement law. And the complement law is going to be 1 minus the probability of 0. So here we have our calculator. In this case, we have our mean of 5. So now, what is the probability of getting exactly 0? This is an example of why knowing 0 factorial is equal to 1 is important. The probability of having no one in front of you in that line at all, not a single person in front of you, it's less than 1%. So in that case, we now have 1. Let me go a little bit further left. 1 minus that, 99.3% chance. So here we use the complement law. So to switch back to our paint, let me share again. Share the paint. In this case, for part B, we want the probability of greater than or equal to 1 car. That's 1 minus the probability of no cars. That is equal to 1 minus, we have 5 to the power of x. In this case, x is 0. So we have 5 to the power of 0 times e to the negative 5 divided by 0 factorial. If you wanted to enter that, you could. For the purposes of the assessment, you're going to simplify that down to 3 decimals. So on the assessment, you have to write down, in that case, you'd write down 0.993. So on the assessment, if you just leave me the thing on the left, you're going to lose like a point or two. You want us to go ahead and simplify it. Because in the real world, you're going to have to simplify it anyways. Are there any questions about the Poisson distribution? The key word is this. This box right here, if you see that, Poisson. Now we're going to talk about binomial. We're going to go a little bit over time. I'll save the hypergeometric for next time. So now we'll do binomial. Let me get that out of the way. So now we have the binomial distribution. And this, we call this B of x. You can make it a P if you want. I'm using B to distinguish that B for binomial, P for Poisson. Then we'll have H for hypergeometric, but we'll do that next time. And this, the formula is a bit uglier. This is equal to n factorial divided by x factorial times n minus x factorial times p power of x. This is lowercase p, not uppercase, lowercase p. And then 1 minus p power of x minus n. I will explain what all these letters mean in a second. Let me just give you a little moment to write that down. Okay. Yes? What's in front of the what? What x? Right here? That's a B. Yes, there you go. Yes, I'm not here to make you memorize every single tiny silly little thing. I'm not here to do that. I'm here to assess understanding. I want to know that you know which one to use and you know how to calculate it. So now let me explain what these letters mean. N is equal to the number of trials. That looks like an N. Let me make that look like an R. The point of the binomial distribution, let's say we're flipping that coin over and over and over again. With that coin, that's going to be the binomial distribution. We're doing it multiple times. In this case, our X is the number of successes. In this case, what we mean by success is just X happening. So let's say we're trying to get heads. Heads is success, tails is failure. Okay? And then finally, P is equal to the probability of X happening. Those are what those letters mean. Again, with the, yes, all these are lowercase p's. Again, for this one, you can use the Desmos calculator to calculate it for you. But again, when you're writing this down in your free response, I want you to show yourself setting it up, simplify a little bit, and then go to your decimal. Like, for example, do not go straight from the formula to the answer. I need to see that you know what you're doing. So now there's a lot of conditions on this. There are 4 conditions. I'm going to write them out, and then explain them. This a little bit to the left. Okay. So I write it down, I'll explain it. We have some number of trials. They're all the exact same. So example, we're flipping the coin. Every single time we flip that coin, the process is the exact same. It's a fair coin. The probability of that coin change doesn't change. We just keep flipping that coin. Now, notice we use lowercase n. The reason why is because we can have much more than lowercase n trials. If we're flipping that coin 10 times, we can flip it 1,000,000 times if we want. Doesn't matter. That's why we have lowercase n. Second, only 2 outcomes per trial. Now, a little bit of a quirky one about this. Oftentimes, you don't have to worry too much about option 2 because how you define the number of outcomes is up to you. For example, let's say you're going to that Whataburger and you just want there not to be any more than 5 people. You could define success as being 5 or less people and failure as 6 or more. So you have a lot of wiggle room with 2. But in the case of heads and tails, that one's pretty obvious. Heads or tails. If you're looking for heads, that's your success. If you're looking for tails, that's your failure. Number 3, the probability of success does not change. Another way of wording this, replacement. Let's say we're picking from that deck of cards. If we pick a card and put it back in, therefore, the probabilities are all the same. If we pick that card and take it out, no, probabilities change. Binomial does not apply. And finally, our trials are independent. 3 and 4 are essentially saying the same thing. They're slightly different, but the general concept is the same. Okay? Now, before I continue, any questions about the general idea of this? Yes? Yeah? How long what? Hopefully no more than 30. No more than 7:30. So hopefully no more than 10 minutes. So I'm going to switch back to Desmos. And in this case, this is where we can get fun. In a good way, fun in a good way, not a bad way, in a good way. So let's close all these. What you can do with the binomial, this capital N doesn't change. The P never changes. The only time it changes if it tells you if it changes. So let's just write down that entire formula. N factorial over X factorial times, notice that button popped up. I'm not going to click it yet. I'll click it in a little bit. N minus X factorial. And now we have times this, where's my P? Oh, it's up here. Times this P, the power of X, times 1 minus P, I believe, yes, 1 minus P, the power, oh, nope, too early. There we go. Power of X minus N. Come on, up there. There we go. Come on. You might have to put the parentheses. There we go. Now, I've written the whole thing out. Add them all. So, let's suppose we're flipping our coin and we're flipping it 5 times and the odds are 50-50. There we go. This is that is a very goofy looking distribution. Oh, did I write that down right? Hopefully I wrote that down right. This is flipped. There we go. Sorry, flipped. It's n minus x, not x minus n. Once again, the right-hand side was correct, both hand wasn't. It's n minus x. That's all. The only thing you have to change. You can see with these, there's a lot of letters. It's very easy to write things down incorrectly. So I'll pull up the paint. It'll show up on the paint when I fix it. This should be the other way around. There we go. So let me fix that on here. I'll just show you all those in person. You can see it. You can see there's just letters everywhere. You can see that one right there. That's the really nasty one. Now, the good thing is I know that one's correct. I checked it about 5 million times, but you can see these letters and formulas get really nasty really quick. So going back to the Desmos is n minus x. So you can see that we have 5. Let's actually make it easier. Let's go to 6 trials so we have an even number. You'll see our peak is at 3. By definition, the binomial distribution is symmetric. The reason why is because of the central limit theorem, which we'll discuss much later on, but binomial is symmetric. So let's do an example. We're going to call this whole thing right over here. Make things. I'll try to make things even easier on you. We say b of x. So now all we have to do is go down here. Let's say we do b of 3. That's the odds of getting exactly 3 heads over our 6 trials. You can see how it makes the notation that much easier on you. This is how I recommend you do it when you're doing the assessment and the exam. The way you're going to want to do it, you're going to want to write down the formula, then plug in the numbers, and then simplify the whole thing down to this decimal. So what are the odds of getting 1 head and only 1 head? About 9.4%. What are the odds of never getting a single head? About 1.6%. You can see how easy this makes things on. So let's go back to the paint, and I will work an example through with you, and then you will do one on your own, and then we will be done for today. Let me share the screen for you. There we go. Notice those of you at home, we switched that to the n minus x. That's where it's supposed to be. Let's go over here. Here we go. It's right down here. I have 2 examples. This is the one I will show you, and then the one up here, that's the one you will do on your own. So toss a coin 3 times, assume the odds of getting ahead is a success. Binomial distribution, what's the probability of every single outcome? Well, we're tossing it 3 times. So here, I'll wait for you to write this down just for a second if you want to write it down. So we're getting ready to switch back over to the calculator. All right, we're going to switch back over to the calculator. Oh, let me pull that back up for you. There you go. All right, let's pull up the calculator. So now in this case, the only thing that changes, we have 3 flips instead of 6. All we have to do, change that 6 to a 3. That's it. That's this. It does all the rest for us. So it asked us to get all the probabilities. Okay. In this case, we can have 0 heads, 1 head, 2 head, or 3 heads. 0 heads, b of 0, 0.125. And if you really want to write the whole thing out, it would be 3 factorial over 0 factorial times 3 minus 0 factorial, which is 3 factorial. And then p to the power of x, that's 0.5 to the power of 0, 1 minus 0.5, power of 3 minus 0. What I'll do is on the whiteboard, I'll write it out after class and post that, but I just care that y'all understand the concepts. So that's our b of 1. Let's try the next one, or b of 0. Now that's b of 1. Only thing that changed is our x value. You notice how easy this makes this on us. And yes, you will have access to this entire calculator for the exam. You also have access to it for the web work, obviously. Yes. Pardon? For this problem, yes, because it asked us for all the probabilities. When we're doing all of these from here on out, we are making the assumption that it is theoretically possible for our event to never happen at all. So the big new thing with our xi's and whatnot is now we allow I to be 0 because we can have it not even happen to begin with. Let's keep going. B2, we change the 1 to a 2, and that's it. So now we have 37.5%, and our last one, B3, will be 12.5%. I'll write down the full calculations on the whiteboard so you can look at that after, but you can see that's the general concept of it. And as long as you know how to set up that whole formula, you'll be good to go. So now, let's switch back to the whiteboard. I will give you one to do on your own. And it's this first one. Let me share the screen again. Here we go. I'll give you about a minute or two to do it here. You can do this by hand. You can do it with the calculator. It's up to you. Choose whichever you prefer. Yes. Yes, that's exactly. Yeah. If we never ever had, that's the same as 0 successes. Actually, you should do example number 7 as well, because that one's the same concept. Now, notice with the binomial distribution, the concept stays the same. If I'm asking you the odds of, say, getting at least one question right, that's the same as saying the odds of, or 1 minus the odds of never getting a single question right. You're going to use that concept for example number 7. I'll give you a little hint on number 7. Let me pull up the calculator here. I'll just make it a little bit easier on you. There you go. That's supposed to be a 2. There's a little hint for example number 7. And then with this, we will be done. You have a question? Okay. We'll cover the hypergeometric stuff and the shortcut for replacement next time. Next time, never even intended to take the full time, so we'll be fine. We'll be fully caught up on schedule after Tuesday. Yes. Yes. We do them over Zoom to minimize exposure. There's one later today. There will be an afternoon one next week on Friday as well. All right, I'll give you another minute. Does anyone need more time? Okay, let's start with our first one. So here we have 10 questions. So we already know right off the bat, n is equal to 10. We want to get exactly 6 right in this case, for this class, 6 out of 10 is 6%. That's passing. So we will know the odds of exactly barely passing, if you want to put it that way. So in that case, we have 6 successes. Now we just need RP. We have 4 possible answers. It's pretty clearly implied there's guessing going on here. So we have 4 possible answers. So you have a 1/4 chance of getting it correct. Okay? Now let's switch over to our calculator and plug these in. So let's switch to the calculator. In this case, our N is now 10. Our P is now 1/4. And we want to know the odds of getting exactly 6. In that case, very, very low chance. About a 1.6% chance of getting exactly 6. The reason why is because if you're randomly guessing, you have a 25% chance. So our mean is going to be somewhere around, in this case, you can see right here, our mean is right around 2.5, 25% chance. And so the 6 value is way off in the tail. And so here you can very clearly see why guessing your way to passing is not going to work. Now, that's that one. Let's switch to the other one. This is our last one, and then we are done for today. Let me share the screen. Here we go. So in this case, our mu is 1.2. Our P is 15%. And we want the probability of at least 2 roofs leaking. It's like x equals 2. So we want the probability. So in this case, this is binomial. The binomial probability that x is greater than or equal to 2. Here's the thing. That x can go, we can go 2, 3, 4, 5, 6, 7, 8. You can go as high as you want. It'll be easier to use the complement rule. This is equal to 1 minus the probability, the binomial probability, that x is less than 2. That's equal to the probability of having no roofs leaking at all or only 1 roof leaking. So that's 1 minus our binomial of 0 using our probability law and the binomial probability of it happening once. Before I go to the calculator, does it make sense where this came from? We use the complement rule here. Yes, you're going to see the complement rule is going to pop up all the time. If you don't understand the complement rule, I will just flatly say you will fail the exam if you don't know the complement rule. It's going to come up everywhere. It'll come up directly like this, and it's going to come up indirectly as well. You need to know the complement rule. So let's switch back to the calculator. For those of you at Zoom, I apologize for having to switch so much, but can't share both at once. I mean, I could share the screen actually. That'd make it easier. So in this case, we fixed 8 roofs. So our N is 8. There's a 15% chance of leaking. And in this case, we want 1 minus B of 0. Oh, come on. B of 0. Stop doing that. There we go. Plus B of 1. Oh, come on. Plus B of 1. And that's our answer. You'll notice it does all the work for you. On the exam, if you say N is 8, P is 0.15, X is, in this case, 0 and 1, and this is our formula, and this is how we use the complement rule. If you do that, you can go straight to the answer if you want. So you could just simply write down N is 8, P is 0.15, X being greater than or equal to 2, is the same as using the complement rule with 1 minus B of 0 plus B of 1. And you go straight to the answer with writing down the formula. I'll take that. I just want to know that you know what you're doing. So with that being that, I will switch over to the whiteboard and write that down, that was about 34%, 34.3%. I think this one was 1.6%. That is all. I apologize for going a little bit over. We just got a little bit backed up a little bit on a couple of the formulas. Sorry for being a bit late. Next time we should not go late at all. And I don't think the time after that will go late either. So next week we should finish early both times. Y'all enjoy the rest of your evenings. Stay safe.